All right, let's continue with our derivation of the work energy theorem. So we got to this point where the net work from A to B is equal to the integral of A to B, from A to B, of mvx dvx plus mv vy dy plus mvz dvz. Okay? And when we take that derivative, we will get 1/2 m all times the vx squared plus vy squared plus vz squared. And you'll take that from A to B. And in doing so, you see that this is going to just be the kinetic energy at point B minus the kinetic energy at point A, okay? Where these are going to depend on x, y, and z coordinates, okay? So the work energy theorem states then that the net work done on a particle equals the change in the particle's kinetic energy, okay? So this is our work energy theorem. All right. So I wanted to quickly go over a problem-solving strategy, which is in the textbook as well. The first thing you want to do, and this is what I've been saying about a lot of the different force problems that we have, is to first draw a free body diagram for each force on the object. This helps you understand what's going on in the problem and proceed from there. Okay? Determine whether each force does work over displacement in the diagram. Okay? And make sure that you keep track of any positive or negative signs in the work being done. Okay? Then you'll want to add up the total amount of work done by each force. Then set this total work equal to the change in kinetic energy and solve for any unknown parameter that you're looking for. Okay? You can also then check your answers, so basically making sure that it makes sense. Okay, and here's a few things to look out for. So if the object is traveling at a constant speed or zero acceleration, the total work should be 0 and match the change in kinetic energy. Okay. If the total work is positive, the object must have sped up or increased in kinetic energy. If the total work is negative, the object must have slowed down or decreased in kinetic energy. Okay, so this makes sense since work is equal to KB minus K sub A, right? So if this is positive, okay, this change in kinetic energy must have been positive. Okay? If the total work is negative, that means the change in kinetic energy must have also been negative. Okay, we have to balance our equation. So these things must make sense, okay, in your problems. So let's go ahead and do an example together. This is 7.10. It states that a bullet has a mass of 40 grains, or we're going to say 2.6 grams, and a muzzle velocity of 335 meters per second. It can penetrate 8 1-inch pine boards, each with a thickness of 0.75 inches. What is the average stopping force exerted by the wood as shown in this figure? Okay. So we need to determine the stopping force exerted by the wood. So this is going to come back to our frictional force. Okay. Okay, so the first step is going to be to use our knowledge of our work energy theorem. which we just defined as our work is equal to K at point B, or we can, excuse me, say our final minus our K at point A, which would be our initial, okay? And I mentioned that we need to take into account our friction or our stopping force, okay? So that would be equal to negative F, I'll say sub S for stopping, multiplied by our distance. So I'll say delta X. Okay, so we'll say that this is the positive X direction. Okay. So our delta X will be our thickness of the boards. Okay, so our thickness is 8 times 0.75 inches, and we need to get that into meters since our velocity is in meters. So let's go ahead and convert inches to centimeters. So that would be 2.54 centimeters per inch. And then we have, per each meter, we have 100 centimeters. Okay, so delta X then is going to be 0.152 meters. Okay. Now, from our equation here, we also need to evaluate this portion here. So we're stating that the bullet passes through all of these and then stops at the very end. Okay. So we can assume that our kinetic energy at the final position is 0. So we are saying that it lost all of its kinetic energy through the boards. Okay, so our kinetic energy final is 0. Okay, so then what we'll do is we will put these into our equation here. Okay, so this is, I'll just say 1. Okay. And we will say it is 0. I'll start on this side. We have negative F sub S delta X equals 0 minus K sub I. Okay. And we'll rearrange that to equal the stopping force since that's what we're looking for. And that'll be equal to K sub I over delta X, or 1/2 mv sub I squared over delta X. Okay, and then all we have to do is plug everything in. So we have F sub S equals 1/2 times our mass, which is 2.6 grams. We want that to be in kilograms, so there are 1,000 grams in 1 kilogram. Okay, so for this guy, we'll say that we have 2.6 grams times 1 kilogram over 1,000 grams. Okay, we can do that real quick. 2.6 over 1,000. We have 0.0026 kilograms. Okay, so we can plug that in down here. 0.0026 kilograms. And you could have left it in a fraction here, it doesn't really matter. And then multiplied by our velocity, which is 335 meters per second squared. Okay, and then divided by our displacement, which is 0.152 meters. Okay, so let's go ahead and do that calculation real quick. And you'll get a stopping force of 960 newtons. So this is our stopping force of that, of the wood. The stopping force exerted by the wood. Okay. All right, let's go ahead and continue to power. So the first thing we want to look at is average power, and that's what we typically would look at. And that is going to be the work done during some time interval. So the average power is going to be the change in work over a change in time. Okay, from this we can then look at instantaneous power, or we can just call it power, which is the rate of doing work. Okay, so power is equal to the derivative of work over the derivative of time. Okay, and we can solve this in terms of work. And so work would be the integral of power times the derivative of time. Okay. Now from this you can see that power has the SI units of joules per second, and we say that that is watts, or big W. Okay, so this is power. Okay. So let's go ahead and use this in an example. 7.11 or 7.11. It states an 80 kilogram army trainee does pull-ups on a horizontal bar. It takes the trainee 0.8 seconds to raise his body from a lower position to where the chin is above the bar. How much power do the trainee's muscles supply moving his body from the lower position to where the chin is above the bar? Okay. All right. So we have some force, right? So we're looking for power. So power is again equal to the change in work over the change in time. So we have our change in time already. That's 0.8 seconds. We need to know the work. Okay. So the work being done. Okay. So when we're looking at work, it is going to be the force times some delta. In this case, we'll call it delta Y. Okay. Our force on this person is going to be mg. Okay, so delta Y. So we can use some estimates. We'll say that maybe he moves up 1 meter, maybe 2, I'm not sure. Let's see. I'd say maybe a meter. Let's keep it simple. We'll just claim that this delta Y is 1 meter. Okay. So then we can plug this in. Okay, so we have our power is equal to mg delta Y over delta T, or 80 kilograms times 9.8 meters per second squared, times our, change in Y, not T, sorry about that. We'll say it's about 1 meter, okay, over our change in time, and we'll say it's 0.8 seconds, okay. So we can put that into our calculator, 80 times 9.8 divided by 0.8, and we get about 980. And again, this is kilograms times meters squared over seconds cubed, okay, or joules per second, or watts. So that is the power of this army trainee. Okay. All right, a little bit more on power. It's involved in moving a body and can be expressed in terms of forces acting on it. Okay, so if a force acts on a body that is displaced in some time dt, the power of that by that force is just like what we just did. So we have dw dt, or f dot dr, or we can rearrange it this way. And so power is equal to force dot velocity.